Hi, everyone. This is Prof. K speaking, and today we're going to talk about distillation and osmosis, which is the second part of chapter 11.4. So our learning objectives in this video are to describe the process of distillation and its practical applications, as well as explain the process of osmosis and describe how it is applied industrially and in nature. So distillation. Distillation is a process where we can carefully heat up a solution so that we enrich its vapor in a component, the lower boiling point, so that we can remove that vapor, recondense it, and get a concentrated version of that component. So ultimately, what this process leverages is the fact that solutions whose components have significantly different vapor pressures can be separated via selective vaporization. So we practice using Raoult's law, and with Raoult's law, what you can do is calculate how much of your vapor is one particular component. And then if you can change your temperature or adjust your reaction conditions so that you enrich it in that component, we can separate it off and we can distill it or create a more pure version of one of the components in the mixture. And so the reason this is really useful in the chemical industry is because we can use it to separate compounds from crude mixtures, and we can also use it to get a lot of different products out of crude oil. So distillation in the context of oil refining is your input is heated crude oil, which comes into your system and is a mixture of both small and large molecules with different boiling points, different volatilities, different viscosities. And what you do is you heat up the bottom of this distillation tower, and it causes the molecules that can vaporize and travel up the condenser. And as it goes higher and higher, you change the temperature of the gas so that at each stage, different sizes of molecules condense, fall out of solution, and can be separated. And so it's a process by which we can use their different vapor pressures and boiling points to heat and then cool compounds so that they come out of a column or a tower like this at different times. And so at the bottom of this distillation unit, you'll have your large molecules that are very challenging to boil, that aren't particularly volatile, and they'll just leave sort of as sludge from the bottom of this. And then as you go up, you get to more and more volatile gases that have different vapor pressures and different boiling points that you can then cool and separate out, so that at the top you can get refinery gas and gasoline, which are smaller hydrocarbons than at the bottom. And so this is really useful, and it's oftentimes one of the first steps that crude oil goes through in terms of processing, so that you can start to use the different size compounds in crude oil for different processes. Osmosis is a bit of a different process, and osmosis is diffusion-driven transfer of solvent molecules through a semi-permeable membrane. And so what this means is if you start in this image on the left, which is osmosis across some semi-permeable membrane, what you can tell is that on one side of this solution, we have a concentration of solvent. And on the other side of our semi-permeable membrane, we have some solute and some solvent. And you might ask, why doesn't the solute cross this membrane at the bottom? And the reason that it doesn't cross the membrane at the bottom is because it's called a semi-permeable membrane, which means that only molecules or ions of a certain size, shape, polarity, charge, or whatever property can pass through or permeate, which is why we call it a semi-permeable membrane, through this material. So in this particular material, the solvent, for example, might be small enough that it can cross the membrane, but the solute here, which we've pictured as larger, maybe can't cross the membrane. And what that causes is that the solvent molecule will initially start to cross over towards the solution side of this process because the concentration of solvent is lower on that solution side. And you'll have this solvent going over and raising the volume of the right-hand side until it reaches some pressure or weight that it can't drive any more solvent further because there's pressure pushing solvent back across. And as I've labeled here on this graph, that difference in height is called osmotic pressure. And so the official definition for osmotic pressure is the pressure, it's when the pressure reaches a value that yields a reverse solvent transfer rate equal to the osmosis rate. So what this means is that the solvent on the pure side would like to move into the solution because the solution has fewer solvent molecules and has a lower concentration. And so that's the process of diffusion. So it would like to go this way, but the weight of raising this water level is pushing back down and trying to force solvent back across because there's weight in the tube. And so when those two forces, or when those two pressures of solvent to move either direction balance, then we reach some stable height in our tube, which helps us describe the osmotic pressure. And the osmotic pressure of a particular system is dependent on the molarity of the solution, this side, as well as the universal gas constant and the temperature at which you're taking this pressure. And so this is something we'll practice using, but ultimately we're looking at the balance between diffusion-driven solvent transfer and this sort of reverse pressure-driven solvent transfer. And when they balance, we get an osmotic pressure with a particular height. We use reverse osmosis, which is that we apply a pressure even greater than the osmotic pressure to the side of our solution with our solvent. And what that does is it forces the solvent here to start traveling towards the pure solvent side, even though the concentration is lower over here. And when we do this, what we're effectively doing is we're forcing this solution to contribute solvent back to the pure solvent side, and we're purifying as much pure solvent as we can. And so this actually has applications in desalinization and other water purification processes, because you can imagine that these sort of blue solute molecules here are salt. And when we apply a pressure and force the solvent molecules or the water to go across the membrane in the opposite direction that they would like to with the osmotic pressure, then we produce clean water and some salt sludge, or some maybe slightly hydrated salt. And so we can use this to get a lot of extra clean water. And so reverse osmosis is used a lot in water filtration processes.